Um, okay, looks like YouTube is on. Um, well, it says we're still sending data. Um, cool. All right, YouTube's online. Twitch sending data. Let's just assume that this is going to get there eventually. So hello everyone. It has definitely been a long time since I've streamed last. I've thought about y'all. Wanted to hop back on. Um, But for those of you who don't remember me, or if you're coming back to check out the stream, my name is Aaron. I am a data scientist. I currently work for the Centers for Medicare and Medicaid Services. So yes, I am a federal employee. Last time I streamed, I was in a totally different physical place. I have since moved. And got a new desk, and then which you can see here, and everything's still kind of a mess, but I'm still working through things. Also, you can probably tell my hair is like a lot longer. So yeah, I will still thinking of making a video to update, maybe more seriously, I guess. But today, what I wanted to do was actually talk about two different things. So it was something I found fascinating at work, because I actually keep hearing stories that in federal government, especially with Medicare or anything health related, we do everything only in SAS. And whenever we export stuff, it has to be done in SAS. I've heard that from so many places, and I actually just like, you know what? I kept I started listening to a podcast called Not So Standard Deviations, and one of the older episodes they actually talk about this and how it's a rumor. And I basically was like, yeah, I have never heard this policy. So one day I just asked in our Slack channels, like, hey, is there a thing that says we have to do everything in SAS? Because I've never seen this before. And like, frankly, there's a lot of SAS use, but I don't know why that would be like no one's opposed to me using Python or R as long as I can explain everything. And the response I got back was, yeah, it's an absolute fallacy that we have to do everything in SAS. Unless it's explicitly stated in the contract, we can use whatever we want to get our work done. So it got me thinking, I think that because, like, you know, things are old, things get ingrained into tradition, and then all of a sudden it just becomes like the truth. I have a suspicion that what actually happened was that Medicare, for example, is such an old institution that we have so much technical debt, and when computing started being brought on in actual workspaces, I have a suspicion that there were too many competing closed source programming options, and eventually someone just said, like, you know what, we're doing statistics here. We're just all gonna get SAS, and we're just gonna work together on that. And I think what ended up happening was that became like the truth in that Medicare only uses SAS. So there is some aspect of, like, we have a lot of SAS users because people, those people all stayed. It's government service, and they stay for a long time, and everyone just gets used to working in SAS. But now it's definitely not required that we have to use SAS. So I think this, like, from a long time ago, people using this stuff, now moving on into the future, generally people seem pretty open to using new things. So if you've ever considered wanting to do data science or coding stuff for federal service, like, know that it's not all old tools that are closed source. There's definitely like a growing proportion of employees who are trying to actually use modern stuff. Yeah. So I just thought that was an interesting discussion at work. And I'll be frank with you, like, I hate SAS. So I definitely try not to use it. So yeah. So what I wanted to stream about today, other than talking about that particular topic, and then I'm also, like, if you're seeing this and of things where something like this happens, where everyone says, like, oh, we have to use this, and it's like, it's not written anywhere, actually. It's not, like, explicitly stated. So is that true? I'd love to hear. Like, I think like one of the more fascinating things, not related to code, is like if anyone can explain to me why the width between tires or wheels is actually like pretty standardized, I'd love to hear that. But if you know things at work, or legacy code or whatever, and you believe that it's like everyone has to do X, and you don't feel it's that way, and you want to tell a story, like feel free to let me know. Yeah, let me know in the comments, or send me a message. You can see my contact info there. Yeah, so today what I wanted to do, I will say that this is partly due to work stuff. When I was applying to be a data scientist back in late 2019, starting in late 2019, going into the 2020s, I had to study a bunch. Data scientists, like, our interviews can cover so much stuff. It's like kind of ridiculous. Like, sometimes you are a statistician, sometimes you're a software developer, sometimes you're a machine learning engineer, and then sometimes you're a product manager, because you have to like make a case for the thing you want to investigate. You have to set up hypothesis tests, so that's statistician. Making a case for what you want to investigate is like a product manager, product owner. Understanding a bunch of the algorithms and stuff used is like machine learning engineering, and then like data analysis of working in SQL. So it kind of depends on the role that you're applying to. It kind of goes all over the place. So I realized that in my entire time at Medicare so far, I've been doing a lot of like policy discussion and also like product ownership. In addition to my main fun work project is actual natural language processing stuff. And that's been pretty cool, but there's a lot of like working through some of the issues and deploying like cloud services and stuff to a group that has never seen that before. But it made me realize that like one crucial thing that I personally think is very important is statistics, and my statistics skills are getting a little rusty. So this stream is actually a technique that I'm trying to utilize from a different influencer on YouTube. She is a data scientist in FANG, and she says that she studies, I think, 3 times a week. Crap, I forgot her name now. I study with a full-time FANG job. I'm pretty sure this will show up on YouTube. Let's go to actual YouTube. Tina Huang. So I will take this video and I will put it in the chat. Tina looks like she is a data scientist, I think at Google. I'll put that, maybe I'll put that in the description. Tina mentions studying with a full-time FANG job. She gets that done. So I guess spoilers, she says that she forces herself to study. And the way she does that is she streams, I think 3 times a week, and just leaves it open for everybody, and just invites people to go basically just watch her study. So that's essentially what I'm going to be doing today. I am just going to go, I've already started like watching some statistics videos. These are my 1 page of notes so far. And I will actually share. I got this from the statistics subreddit. It is a data scientist who's now working, I believe, in the DC area, and was a PhD student / lecturer, I think, at University of Utah. So this is going to be the source material, source lectures. And I got those from, I got the lectures from our statistics subreddit. Oh, actually, so this is partly why I'm typing a little slow. I got one of these from Falbatech. I think I might have showed it before, but well, okay, half. So that's the other half, right? This is a mechanical split keyboard. So like sometimes it takes a little getting used to, especially if I've been typing all day on like a regular keyboard. My work keyboard is not connected to this thing, so I just it's a struggle sometimes. But yeah, so my goal is to go through these videos, and they're very basic. They're like an intro to statistics, and I'm trying to like totally refresh my memory. Honestly, a lot of it has been like super easy, but it is nice to like actually see some of the process go through. And the reason why I'm starting from like these basically first principles is because honestly, like that's kind of how you set up like baselines and stuff, right? Like even when you're doing machine learning stuff, like you can always jump to a neural net or whatever if you really want to, but like why would you do that? They're very difficult to deploy. They're difficult to understand. They're quite abstract, and they require usually a lot more like processing in terms of your code to actually get things working. So like if you're trying to build a classifier and you jump to a neural net to try to get your classifications correct, that would be, I would say, is the wrong path to go. Because you could just as well have started with like a logistic regressor, and that's, you know, really simple to deploy in like scikit-learn or stats models, I guess. I think they have one, maybe not, but they're really simple to deploy. And then if it turns out like that works basically just as well as a neural net, then you just saved yourself like a ton of time. I think I commented on an earlier stream that like there was someone who used a neural net to classify the recipes, same database that I was using for Melion, and like I looked at it and was like, hey man, this is actually worse performance than my simple logistic regressor. And like he never did a baseline comparison, so he just deployed a neural net for, I guess, experience, but like I don't know. Yeah, so I'm starting to relearn / refresh my memory on statistics, because some of these things they like actually help explain some of the theory behind the more advanced algorithms that power a bunch of the stuff that like, oh, we use like this to describe different sets of, you know, let's say we're doing a hypothesis test, and we've made an assumption and don't even realize it because all we did was like we just jumped into doing the test. I guess one simple thing is like, you know, if your data is not normally distributed, quite a few, I believe, ways to clean the data start failing, because like those actually assumed a normal distribution to your data. So going back and like making sure I remember a bunch of these things, at least to me, is like pretty helpful. I think I'm peaking a little bit on my volume, so I'm going to fix that. Yeah, so that YouTube playlist is what I'm going to be going through. When I started watching these yesterday, I didn't have my notebook, so I just grabbed like a sheet of printer paper and just started writing stuff down. So what I'm going to start with is basically converting these over into an old notebook that I just found, and just try to keep things more organized, because like I like sheets of paper for quick notes, but if they start turning into multiple pages like this, it will drive me crazy. And I think, of course, I almost forgot a pen. So yeah. So I will open up this playlist and then have it ready. And in the background, I've also got just like a simple streaming playlist on. It is that lo-fi stream beats thing. So yeah, okay. I think we are. I should probably sign into my YouTube account and make it easier to follow along. Let's see. Can you see my type? Oh, you can't see me type my password. That's cool. All right, so I don't have to do anything. If I can't even remember my password anymore. Maybe not. Oh no, my second factor. Hold on, I'll be right back. uh,
Variance is in units squared, but the standard deviation is in just the same units as the data set. So these are good properties to be aware of. Okay, so the sample variance and standard deviation.
okay, cool. I'm back. I got my phone, did my second factor, logged back in, and automatically started auto-playing. So let's do the first things first. We're going to convert our old notes. So started on the January 22nd, 2022. So it was, what was the original book? All right, so source book, which I actually forgot to write down before, was probability and statistics for engineering and the sciences. It's the 9th edition by J. DeVore. And if people have a preferred statistics book, I would also love to hear. Statistics always has seemed like such a weird thing to me. I can learn it. If I'm not actively using it, just like a language, I will forget it. Oh yeah. So normally, my go-to for these sorts of refreshers is actually Coursera, where I think I actually have a membership there. And Coursera in the past has been really great, but one of the things I noticed with statistics, and I think I came across this last year, is that I found it very hard to actually find a true statistics course that was free. um, or even paid actually. Coursera, when I tried to search for, just give me like a statistics refresher course, their intro to statistics class as taught from Stanford University is actually more like an applied statistics class, in my opinion, because it almost immediately jumps into things like using R to do a bunch of regression stuff. And it's like, okay, I understand, but like we're skipping over like a whole thing where you're basically like trying to set up experiments, or even just understanding your data. So it just seemed odd that it was more like statistics as being applied to analysis instead of like an actual statistics course. So I tried to search for, I think I searched for like half a day in between work meetings and just work in general. And I was like, wow, this is like super weird. And eventually it's how I ended up like, let me go ask the statistics subreddit, like, what are your good free resources for refreshing your stats knowledge? And there's a poster there who just said like, hey, I uploaded this whole series of lectures. And I was like, frankly, this is going to be better than anything else I've got. I don't know if it's perfect, but just get started and then catch up later. Yeah. So one big thing with this is that the labs and stuff are all done in R. I will be doing it in Python. So there's going to be a little bit of conversion over, but in terms of the actual lectures, that part I think should just be fine. So yeah, the originally found on r/statistics. And okay, so let's begin. So chapter 1 was overview and descriptive statistics. And this was honestly, like, if you look at my notes, they're pretty lackluster because there's some things that are like, well, let's just define the mean, which is fine and all that, but not exactly stuff I don't remember. So chapter 1 is overview and descriptive statistics. Section 1, populations, samples, and process, according to the lecturer. So we've got basic terms. We've got data. Should be pretty obvious. This is a collection of facts. Population is a group of interest. A census, which is data from or for the entire population. And one of the things is that it is almost impossible to go get data for the entire population. It is too expensive, and let me move this aside. It is too expensive, and it is like very time consuming. Yeah, it's expensive in like almost every aspect of the word. So like, I'm American, right? So like, imagine trying to survey all, what are we at now? Like 380, 400 million American citizens, and just ask them questions. It's not going to work. And like, even if you're just going to interview everyone in your town, right? Unless there's like 50, say, even if you live in like in a rural town that's spread out and there's like only 50 residents, you have to actually go around and talk to all the people. So I don't know, even if there are only 50 people in the town, depending on how big that town is, that might take forever. Yeah, so the reason why we've got population and census, and why it's a big distinction to say like a population is everyone, is because it is impossible to get data from everyone. So instead, we actually take samples. So samples are data for a subset of the population. And an observation is an individual data point. And these observations make up a sample. Probability. Oh yeah, so it's very cool. This lecture actually made a distinction between probability and statistics. So in his notes, he actually says probability is when you know the population, probability will tell you how a sample will behave. And statistics says, given a sample, how can we infer the properties of the population, right? So it's a very big distinction there. I don't know. I thought that was pretty cool. But I'm a nerd who likes kind of these technicalities. So yeah, probability, if you knew the population, how will a sample behave? And statistics, given a sample, how can we infer properties of a population? And I don't know. I kind of like taking these classes again and doing things on paper. It just reminds me of uh, when I was an actual student. I actually kind of want like a little digital tablet that would back everything up, but I don't know, just something about like actually using pencil or pen and paper is nice. Um, yeah. So another thing about like why I want to start from basics, or to remind myself of all this stuff, is like I don't know, you just get refreshed on maybe the correct way to do things. So one of the things that he talks about is that there are two approaches for collecting data correctly. There's a simple random sample, which is basically as described. You literally just randomly sample. And this is the focus of this particular class because it's the easiest case. And this is abbreviated as SRS. And two is the stratified sampling method. And in this way, you take a population, you divide it into observable strata. I made this mistake again. Okay. Maybe I should be doing this in pencil instead of pen. So simple random sample. What I did in the previous on the sheet of paper was I wrote the two forms and then wrote the examples after. And then I think the nicer way is to just write each type. So like write, what is a simple random sample? An example of a simple random sample is to take the overall registered voter list and literally randomly just pick people from it. No distinctions. So SRS example, take overall registered voter list and randomly select people to poll. The second one, stratified sampling. The population is divided into observable strata. And there's one thing here that's actually fairly nuanced, is how do you define your sample or your population, right? So in this particular one, it looks like the population is just the overall registered voters. And that's important because when you do the stratification, you have to specify this out. Because like you can argue based off of the strata that are about to come that you could have reduced it to be a smaller population, and then it's not actually stratified sampling, right? So the example for stratified sampling is instead of taking you take the overall sample, you then divide that whole list into by state, and you take an equal number of voters selected from each state, and then you poll those people. So that's different, right? So like if you were to do a simple random sample on the entire list, just based off of the total amount of people living in the United States, right, you'd have a lot of people that could be picked from the populated areas. So that would be New York, California. Actually, I think California, then New York, Texas, and Illinois, I believe, and Pennsylvania. It would basically just completely, the odds are not high to pick random people from like quite a bit of the center of the country, and also the Alaska and Hawaii. But with the stratified sample, you have to pick 50. Like there are 50 categories because it's one for each state. And then from those 50, if you're picking, like if you want to talk to 300 people or 1,000 people, like now you're doing 20 from each state, right? So that's stratified sampling. So I'm going to write that down. Equal number of voters selected from each state who, now underline that, from each state who are then polled. Forgot the word example in my notes. Man, I forgot. It's difficult to write and talk about what you're writing about at the same time. So one thing with unfortunately, I think you said they're not really going to talk about the stratified sampling example, but he makes a comment that stratified sampling can actually increase the statistical power of an experiment. So what does that mean? Well, practically, it means that you can actually... what does that mean? I knew yesterday when I wrote it down. Hold on. Can increase statistical power. So it's basically, I think it's there's a mathematical relationship between statistical power and the effect size. But the important thing is that you can actually reduce the amount of data that you actually need to collect. So you can make a impactful test without gathering as much data, which is always expensive. And I think like later on we'll go over the term statistical power. Reducing amount of data needed. And actually, I will just go ahead and say statistical power, and we'll just look it up together. There's no shame in not knowing something or forgetting something. Statistical power. Statistical power or sensitivity is the likelihood of a significance test detecting when there is actually one. When there's actually an effect. I think that's what they meant. So we'll just put that in here. First hit on Bing, I think. Yeah, and then it says a true effect is a real non-zero relationship between variables in a population. An effect is usually indicated by a real difference between groups or correlation between variables. A high power in a study indicates a large chance of a test detecting a true effect. Low power means that your test only has a small chance of detecting a true effect, or that the results are likely to be distorted by random and systematic error. And yeah, actually similarly, that talks about the significance. There's a very explicit definition for what the significance, like that alpha actually means, or sorry, p-value. And they talk about on not so standard deviations that no one actually uses the whole definition because it's longer than to say a shorter form, and the shorter form always introduces some like space for interpretation. So they said to try very hard to always use like the full definition of that term. But yeah, we'll just say for now, we'll just write down and then move on with the rest of the notes. Or sensitivity is the likelihood of a significance test detecting a true effect. Cool. All right, and that was actually all the notes for section 1 that I wrote down. The rest of it was more logistical for the class. So section 2, pictorial and tabular methods in descriptive stats. And there were some more terms here. So distribution. Most of this was drawing out plots, so I did not take as many notes. Distribution describes what values a variable takes and how frequently it takes them. So variable here is defined as basically any of the things that you're kind of looking for. So for the voter population, for example, like a variable would be they're like a person's age, gender, salary. Yeah, depends on what you're looking for. Yeah, so I think like one of the things I wrote down from this section of the pictorial and tabular methods was stem and leaf plots, because they seem like they're the origin for actually doing histogram. And basically what you do is you take your data, it doesn't even have to be ordered, and you find bases for the data that can be used to differentiate the different nodes. So with the sample data, it was actually the heights. So the heights were reported in where integers, or the ones place for decimal numbers, was feet, and then the fractions, not fractions, the tenths, hundredths, etc. places were a proportion from feet. So it was like 5.03, right? So it'd be 5 feet and 0.03 feet. And you would think, naively, like you could make your stems the feet, and then the decimal places your leaves. However, you run into a huge problem because it turns out most people are within a certain height range. So most people will be 5 foot something, right? So what ends up happening is if you make your stem 5, you'll have very few people in the 4 or less, and then very few people in the 6 or higher. So your eventual stem and leaf plot is, or stem and leaf table, is not very helpful because all the data is compressed into like one stem base. So for the heights, it's actually better to go 5 point something. So it'd be 5.0, 5.1, 5 point, etc. And then after that, your leaves would be like 1, or 0. So you would have 5.0 as a stem, and then the leaf would be 1, so you'd end up with like 5.01. And then you do that for your whole data set. And because this particular example data set actually only 2 decimal places, you're very limited in the number of actual combinations you can get. And that is really nice, right? Because like everything will be consistent. And then in a worst case, in a situation where everyone, it's all completely evenly distributed, and you just have like a flat distribution, that just means that already tells you like everything's equal. But otherwise, like you do get counts essentially. So yeah, so stem and leaf plots, find bases or stems for your data that can be used to differentiate leaves. This is the basis for a histogram. And then the important thing is you have to draw a vertical line that separates your stems from your leaves, and you also have to describe the units because otherwise it doesn't really mean anything. So right, it'd be 5.0 vertical line, and that's feet. Yeah. Use a vertical line with units to separate stems from leaves. Okay. And then still in section 2, we've got a dot plot. And these represent each data point along a number line, stacking repeats. And then that led into histograms. But one concept that was interesting, because I at that point, going over the different plots, I did zone out a little because I was like, I've seen a bunch of these before. I saw one thing that I thought was interesting, which was the idea of binning for histograms. So the when you have a histogram, you have a number of samples n, right? So n could be, let's say, 100, right? Sometimes you ask like, okay, well, how big should each bin be, right? And the explanation given was usually people will say, well, why don't we try the square root of n and use that many bins, or make that like the bin size. And that it seems to be like a matter of convenience. Because it turns out he referenced this but didn't provide a footnote, and I'm kind of interested to see the source. There's apparently like a mathematical proof that says it would be better to actually use the fifth root of n. And I was thinking like, oh, I talked about this with my brother, and we're like, oh, that's interesting. Like, how big would your bin size be if you had the fifth root of 100? And it's like 3. So you end up with like 30 bins, I think, 33 bins. Yeah, I really want to see this proof because it was like, well, that's pretty wild. Yeah, I think I'm interpreting that right. I think he may have said like, I don't think he said the number of bins should be the fifth root of n because that's like too few, right? So yeah, binning for n samples. Rule of thumb is to make bins of size root n, but it may be better to use bins of size n to the 1/5. Yeah, and then in looking at histograms, there was an investigation into using the number of modes present to see how that influences your bin size selection. So if your data is multimodal, it's possible that you actually picked too few bins. And the reason given was having multiple modes implies that there's actually more than one population in the data set. So the example he gave was if you're looking at heights, you will of the entire population, you'll see two modes, because there will be one around 5'4" and one around 5'9", right? And all you've really done is you've accidentally shown that generally men and women are of different heights. Yeah, so multimodal, ask if you have chosen too few bins, multiple, and this ties back into like, how do you define what your population is, right? Multiple modes implies more than one population. In your data set. And then I wrote the rest of this particular lecture as a walkthrough of various plots and then how to make them. So it was a lot of just like drawing things out and like talking about skew. Yeah. So the next section, section 3, measures. Oh, wow. I started the word measures with S. Measures of location. And then this section, there were things like the mean, median, and quantiles. And then in the notes, it says mean is less sensitive. Oh, whoops. I was like, that's not right. Median is less sensitive to outliers. I skipped a line in my notes. The median is also preferred. It's also preferred for skewed data. The mean is preferred for symmetric data. And he actually gave a funny example of like, if you were, and you know, the preference is dependent on the situation. So he gave this funny example of, let's say you tried to win the lottery a bunch of times. Let's say 10 times, and you won 0 times, or you won 9 times. Oh gosh, you lost 9 times, so you got $0. And then on the 10th time, you won a huge payout. So in that particular case, would you prefer to take the median value or the mean value, despite it being like heavily asymmetric data? And of course, the answer is, in that case, the mean, right? Because the mean of, say, $1 million and 0 9 times is still, $100,000? But if you were to take the median, you would get 0, because 9 of those data sets are 0. Yeah, so I don't know, it just seemed like a funny example. Yeah. And then this particular lecture introduces the concept of the trimmed mean. And the reason why a trimmed mean is it is supposed to help address some of the issues around both the median and the mean. So the mean could maybe be too sensitive to outliers, which is a problem. And then the median may be too sensitive to let me see. I just summarized it as trying to reduce the problems of both using the mean or the median. So I'm to review that section of trimmed And maybe now's a good time to actually just hop back into the lecture and then try to follow along, because I have to rewind to figure out some of the other definitions. That was weird. The sound wasn't coming through, so that was super weird.
This video, I recorded it a while ago, and it just stopped us. And let's start with data set one, which got covered
Okay, so if you want to know where I am here. Now I'm just following along with the lecture. Oh, the reason, so I would screen share this, but I think technically that violates the terms of service for both Twitch and YouTube. Definitely for Twitch, because I think you're not supposed to share content from another website, especially one that competes with them. So I can't just like put the video up here. Otherwise, like I could get flagged, and I don't want to get in trouble. So he's pointing out he's got three different data sets that they all have a mean. They have the exact same mean, but the data is like not not all clustered around the same location. So with one data set, the mean is 6, but all the points are within like 3 of each other. On these other ones, like there's one has outliers and one has like larger gaps between all the individual recorded points. And he's pointing out like, well, maybe in this case you can see that the mean is not a sufficient way to describe the data, which is true, right? Especially if you're trying to look for, let's say these measures, these variables represented physical measurements of something coming off the production line. If there's so much variance between all the different things that come off the production line, that's pretty bad, right? Like things are too big, things are too small. Yeah. Actually, I'm going to hop away for a second. I'm going to get some water.
by the sample size and then multiplied by the sample size again. So we end up with nx bar minus nx bar, and that equals 0. So what that means is that this quantity is always equal to 0. Always equal to 0. I think I found a dead spot on my screen.
Okay, I am back. So mathematically showing that the first guess at a definition for deviations is not the correct one because everything turns out to be 0.
Alright, what I just said was literally close. They don't always have the same sign. In fact, you have opposite signs. You have some positive, some negative deviation. And it turns out
And we're going to go for a ride because I want to stand up for a bit. Welcome to fancy sit-stand desk world.
try this. Replace parentheses with absolute value. And now you don't have that issue of negatives and positives canceling each other out. And that makes sense. The thing though is, this is actually going to from a mathematical perspective. And the reason why is because it's involving absolute values, and absolute values are not differential. Absolute values are different. They have a tusk. A sharp point. Sharp point on top. Compare that real top to, so this is like the absolute value of x. Compare that instead with the function x squared times that jar. That has a nice feature of being differentiable. So what actually statisticians end up doing is they say we should add up
So be that guy,
sum
the one who shows
from
up
I
with a gift that'll
equals
take
1
her breath away.
Now you have a
n
friend in the jewelry business.
xi
Shane Company and
minus x
ShaneCo.com.
squared. And this quantity is known as the sum of squared errors. Xi minus x bar, a term that statisticians like to use for that, is an error. And we're adding up the squared errors. And there is, in fact, an interpretation for the square part, which is maybe remember, this is how I like to think of it. I think that this formula kind of rhymes with x1 minus x2 square plus y1 minus y2. Remember that? Do you remember that from geometry class? If you take the square root of this quantity, you end up with the distance. For Euclidean distance.
So now the
And
defining the
take
what
actually
turns out to be the sum of squared errors. So to try to get around the everything going to 0 to in terms of deviations, originally tried to do absolute values, or the absolute value of the deviations, but that is not differentiable and becomes a mathematical problem. So now squaring them, because you still need the signs to be consistent, they can't cancel out, but that is a differentiable property.
we would have the average squared distance. Now, that's actually a good idea, but there's a better idea, which is to divide instead of by n by n minus 1. Now, that might strike you as a little bit odd. Why is it that we're dividing by n minus 1? There's a few reasons for that, some of which we'll talk about later in chapter 6. But n minus 1, there's actually a chain of 2, and it's known in this context as the inverse of
So when you take the sum of squared errors, you divide it by n minus 1, which is your degrees of freedom, and then that gives you your variance.
Now, maybe you recall from previous sections my saying that there is a sample. We have to talk about a population mean, and there's a sample mean if you talk about a population mean. And there is a sense in which the sample mean can estimate.
And in this case, it's a sample variance.
Sample mean, yes, nice population variance. So the sample variance should estimate the population variance. There is, in fact, a population variance. Here's the thing, though, about the population variance. Our estimator, if we were to divide by n, would have a tendency to decline. I mean, it would still be close to the population variance, but it could be a little bit better by dividing by n minus 1 instead of n. If you were to divide by n, you'd actually be a little too small. So we should divide by n minus 1 instead. There's a term called biases that we will discuss more in chapter 6. But long story short, it turns out that when you divide by n minus 1, you have an unbiased estimator of the population variance. Whereas when you divide by n, there is a very small bias. Now, that said, you can still divide by n and have a reasonable estimator. It just will have that bias problem. The bias gets really small as you increase the sample size, but it is still small. So why not just get rid of it? So these are some potential arguments for why you should divide by n minus 1. And later on in that chapter, we will actually, I may actually show that the expected value, you divide by n minus 1, you can get the sample variance. But we're a long ways off from that. So accept it that you pretty much have
Some
defined
teasers for the future chapters for mathematical definitions.
as like an average squared distance. Oh yes, another argument for why you should be divided by n minus 1. When you compute the variance, there's something you have to do first. You have to compute the sample mean. You have to compute the sample mean first, and there's a penalty that you have to pay for that. The term degrees of freedom means that this is basically the number of observations in the data set that you are allowed to change. And where if you can change those observations freely, and you can still end up with the same sample mean. Because it turns out, for basically the reason that I showed up here, this line of reasoning, that if you know n minus 1 of the observations and you know the sample mean, then you know the nth observation that you needed to test out the data. So a sample mean contains information, and the fact that you had to estimate a parameter before you could estimate the sample variance is a reason why there's a penalty for sample size. So it's inappropriate to divide by n minus 1 navigate, or to divide by n, and I think we need to divide by n minus 1. Alright, now here's the thing about the sample variance that we still define. Think about the units of these things. Let's say that we were talking about going back to, or even for this soccer data set that I've seen in a few videos.
Excuse me. Ooh. And he's saying there's one major problem with looking at the variance, and it's that it is a squared term. So your units become squared, which doesn't really make any sense. He's talking about soccer goals, and like goals squared, what on earth does that mean, you know?
But then you square it, and you end up with goals squared. What the heck are goals squared? That's a unit that doesn't mean anything. We don't like the fact that in the end, the sample variance produces square units. We would rather have an estimate, a measure of spread that is in the same bin as the data set. And there is such a thing called sample standard deviation. So the sample standard deviation is S.
And that is why we end up with the sample standard deviation, which is the square root of the variance. Now it's doing an example in R code.
A vector will tell you how many objects are in that vector. There's also a function called summary, which will give you some basic statistical summaries for a data set stored in a vector. Or actually, summary is summary will give you some basic statistical stuff that we're going to leave that for later on. For now, it's just giving us some basic statistics for a vector. And I'm now going to compute the sample variance of this data set. Okay, so I like to create a table when computing this by hand. If you don't want to watch me compute this by hand, because it is kind of a tedious calculation. If you don't want to watch it, this is a part that you can skip over. All right, anyway, so we have 12 observations in our data set, so I'm going to start numbering off 1, 2, 3.
So he's about to calculate the standard deviation and the variance, and he's like, I'm going to do this by hand, so it's going to be tedious, so go ahead and skip. So that's what we're going to do.
Minus 12, which is the sample size, times the mean. All right, we need to compute the mean. So the mean is going to be the sum of the observations, which is 62, divided by 12. So in this parentheses, I'm going to put 62 over 12 and square it. And you plug it into a calculator, and the number that you get for the sum of squared errors is 197 divided by 3. Which is, as a decimal number, 65.6, where the 6 is repeating. So the sample variance will be the sum of squared errors divided by,
Let us introduce you to
as a
Monday.com
reminder,
Work
the sample
OS.
size minus
With our
1,
intuitive and
which is
powerful
going to be
platform, you'll start hearing
65.6
and you got it in no
divided
time.
by 12 minus 1,
Monday.com
which is
gives
11,
any team a
which is
unified
equal
place
to
to run their work, track impact, and take
5.9.
success to the next level, no matter your industry
where
or
the
company
96
size.
itself
Go to
is repeating.
Monday.com to start
Now,
your free trial today.
This is nice, but the thing is, the sample variance is in the units of the sample
Did
variance
you know
is little
Amazon
squared.
provides
We
ways
don't
of
like
working
that.
that
They
fit
want to
your
keep the standard
lifestyle?
deviation
They
too,
know
because
you
that's a
value
more
your time
interpretable
outside
number.
of work,
The
juggling
standard
family,
deviation is going to
school,
be the square
friends,
root
or other
of the variance,
activities. That's why they
which is
offer a
going to
variety of
be
shifts that
about
work for you. There are full-time, part-time, and even temporary opportunities that can
2.443.
work with your schedule,
Running
with
the 3
great
decimal
starting
places.
pay and
So,
sign-on bonuses. If
you
you
can
want a
think of this
career that
as
fits and
your
adapts to your
daughter's soccer
lifestyle,
team
head to
is varying
Amazon.com/apply.
around their
Amazon
average
is a proud equal
score of
opportunity
about
employer.
5 points, but they're deviating from that by about 2 points. So on average, they'll be about 2 points away. Okay. All right. So in R, the functions that are responsible for computing these quantities are var and SD. R computes the variance, and SD computes the standard deviation. So var of the soccer data set is basically what I wrote down, and the standard deviation is basically the same thing too. All right, so the sample mean, so for the sample variance, we actually have some nice properties that also translate into properties for the standard deviation. Actually, before I continue on, I'm going to double check, because this scares me. Okay. Okay. Everything is good. That scared me. Okay. So, some basic properties. Let's suppose, in this proposition, let's suppose that we take our data set and then we shift everything by a constant to produce a new data set that's shifted by a constant. It turns out that the sample variance for the new data set will be the same as the sample variance for the old data set where you didn't shift. That's a good thing. What that means is basically this is, in fact, a measure of spread. If it wasn't a measure of spread, well, basically, if this was not the case, if the sample variance changed by shifting the data, then it doesn't seem really fair to call it a measure of spread, because it's also capturing location too. But the fact that you don't have to, the fact that it doesn't care about the location, or in a way, it doesn't actually care about the mean, because, and you can think of that as because it subtracts the mean out for the data set. The fact that it doesn't care means it is in fact a bona fide measure of spread and not measuring something else
rescale your data set by C, the variance will scale by C squared, and the standard deviation will scale by the absolute value of C. So the standard deviation is always going to be positive. The variance will always be positive. So when you rescale the data set, it's not going to, whether you multiply by a positive or a negative number doesn't actually matter. And also it tells you that if, like, you can think of this as saying something about unit conversions. Because remember that unit conversions generally are multiplicative operations. If you wanted to change the units of the standard deviation, you could do so by just multiplying the original standard deviation by whatever unit conversion formula you have. And also this is basically telling us what I was saying before, that the variance is in units squared, but the standard deviation is in just the same units as the data set. So these are good properties to be aware of. Okay, so the sample variance and standard deviation, these are one class of estimator of spread. They're not the only one. Oh, by the way, we did have this discussion when talking about measures of location about biasness. No, not biasness. Sensitivity to outliers. It turns out that the sample mean and the sample variance and sample standard deviation are also sensitive to outliers. In fact, they are more sensitive to outliers than the mean is. So they care a great deal about outliers too. Just throwing that out there. And you can kind of tell by looking at those formulas, since when you look at them, they're basically means, right? They're averages, or at least the variance looks like an average, and the standard deviation is square root of an average. So if you end up having a very large error, then that's going to make your variance very large. So it's sensitive to outliers. Just mentioning that. Another measure for spread is known as the fourth spread, or sometimes, like in Math 1070, we call the interquartile range. It is the third quartile minus the first quartile. And we're going to denote it in this class with FS. This is another measure of dispersion. So let's compute the fourth spread for the soccer game scores. We already computed in a previous a great deal about outliers too. Just throwing that out.
All right, so now talking about a different measure of spread called the fourth spread, which is, this is known as the interquartile range and is the third quartile minus the first quartile. And is denoted as F underscore S. It's a measure of dispersion.
Look at them, they're basically means, like they're averages, or at least the variance looks like an average, and the standard deviation is square root of an average. So if you end up having a very large error, then that's going to make your variance very large. So it's sensitive to outliers. Just mentioning. Another measure for spread is known as the fourth spread, or sometimes, like in Math 1070, we call the interquartile range. It is the third quartile minus the first quartile. Again, we're denoting in this class with FS. This is another measure of dispersion. So let's compute the fourth spread for the soccer game scores. We already computed in a previous video the third and first quartile for the soccer game measures. So the fourth spread will be third quartile minus the first quartile, which actually turns out is at 20%, which is equal to 4. So the fourth spread is, in and of itself, a measure of dispersion. And one way statisticians might use the fourth spread is as a tool for outlier detection. Remember, we care a great deal about outliers. If there's an outlier, we would like to have outlier detection tables, because if there is an outlier in the data set, we would like to be able to decide how we should approach it.
And he said this is used for outlier detection.
So we would like to be able to detect them. So we might call an observation that is further than 1.5 times the fourth spread from its nearest quartile a mild outlier. So as an example,
Something
suppose you have a data set. Our data set looks something
1.5 fourth spreads away
also got a couple observations.
from
Those two observations
the
look like an outlier.
nearest
Let's suppose
quartile.
we have
is a mild outlier.
Let's suppose that our first and third quartile.
3/4 spreads away is an extreme outlier.
If that is the case, the fourth spread, or the IQR, is going to be the distance between those two fourth spreads. The distance between those two fourth spreads. So according to this rule, how you detect an outlier is you take this one and then increase it by 1/2. So 1/2. And go beyond, and you're gonna like see compare an observation to its nearest quartile. So these are going to be close to the third quartile because they are above the third quartile. And you compare, see if those observations are 1.5 times the IQR away from the nearest quartile. And if they are beyond that range, then they are candidates to be outliers. So these are now starting to look like at least partial outliers. But in fact, if we were to double that quantity, so 3 times this, turns out that they are beyond 3 times the fourth spread as well. So now these are looking like extreme outliers. We can also do the same thing on the left-hand side of the data set for outliers that are numbers that are really small. There's nothing that says that outliers have to always be large numbers. They can also be really small numbers too. And there's no outliers on the left-hand side of the data set. I should point out, this is technically for students to think that why is easy with the definition for outlier. The word outlier is intentionally vague because there's many different ways you can define an outlier. This is one
He's pointing out
or one such criteria.
the definition for outlier is intentionally vague, and this is only one way to determine if something is an outlier.
The criterion does not work if we were to go into 2 dimensions. It is a one-dimensional approach, not a 2-dimensional approach. And we can still have outliers in 2 dimensions or in bivariate data, and you can still have outliers there, and they're going to be there's more possibilities to all of these approaches, as opposed to just more ways for things to be outliers. So I'm hesitant to just let students think that this is what an outlier is. There's actually different ways to think about outliers or different definitions based off of our problem and how we want to approach it. So we can choose a procedure that is tailored to our problem to find an outlier. So this is what we're using in this class, but it is far from like what we always use. It's not really the definition of an outlier. We would just say an outlier is a point that seems unusual to the other ones, that seems to be distant in some way from the other ones, or it doesn't seem to follow the same pattern as the rest. Okay, so moving on to example.
Sorry about that.
Detect outliers in Socrates. What are the means towards the inversion? Mild outlier or extreme outlier? So fourth spread, you have to recall, was 4. So 1.5. So 1.5 times the fourth spread is going to be 4 times 1.5, which is going to be 6. And 3 times the fourth spread is going to be 12. So let's see what it would take for something to at least be mild. To
whiskers out to the observations that are not outliers. So the largest observation that is not an outlier and the smallest observation that is not an outlier. The outliers are treated differently. They get their own points in the box plot, kind of like with the dot plot. That's more complicated to do, and I'm not going to ask you to do that. Using just the 5-number summary and extending out to the maxima is fine for me. And I feel like that if you were ever to draw a box plot by hand, you should just keep things simple, because it's not too hard to compute a 5-number summary especially if you had, say, if you had like a 7-leaf plot. But a box plot, like computing the outliers is a bit much. So, a box plot on its own, I mean, it's okay, but a box plot really shines when there are other box plots with it. And when you have that, you can now start drawing comparative box plots. And when you have comparative box plots, you can start to say things about the relationships between different groups that
Right now, talking about the advantages of using box plots, specifically multiple ones, so you can actually compare different different data, or yeah.
So you can have a box plot for n times, and you can have a box plot for width times, and then you can make comparisons, and you can compare. In this case, this looks like
Or different samples.
So one thing that you can do when you have compared to box plot is compare the location of the boxes. You can also compare schools of thoughts. So for example, if you saw one box plot that looks like this for one group and a box plot that looks like this for another group, you might say that those two groups certainly have different schools. So you can start making comparisons that are more easily made with plots such as these than you would, say, try to overlap density plots or something. So comparative box plots are great because they allow you to, at a glance, compare two different groups and their distributions. So let's go ahead and start creating some box plots. In this example,
And now he's going to start making box plots, so I'm going to skip ahead because we don't need to hand calculate these and then draw them. Yeah. I think that is actually the end of, so I'll just write in here, like, time spent and calculating variance, standard deviation, spread, fourth spread. Outlier determinants. And drawing box plots. And then that would finish that lecture. So I'm going to move on to the next one, which is set theory.
hey students,
Oh, cool. This is actually chapter 2. So I'm going to start a new thing. So chapter 2, and it's actually probability. I spelled that wrong. Probability. There we go. I do wonder, because I think he did not fully finish each chapter, so I kind of wonder what was skipped over. Oh, no, that's not true. Basically, this lecture, like, left blanks so people could fill in as they're reading along or studying along. Yeah. Um, I think so. I've been streaming for an hour and a half. I think it is a good time for me to take a break and stop, especially since it's a brand new chapter and it's about probability. And I think it's time to try to figure out what to get for dinner. So yeah, I will check in later and probably stream more. I like that I have to actually study these things and explain them, while on camera. Um, yeah, I'm actually wondering where did I get. That's weird. In my notes, I write about trimmed mean, and I have no idea which lecture this actually comes from. Um, let's see. Let me actually try to find this thing because it's going to drive me crazy.
Measures of location. In real data, that's never the case. In real data, to
Oh, it's in the previous lecture.
detract from the overall score, then it becomes trouble. On the other hand, median indicates
So that was in location measures.
you care more about what
And I see what happened.
wow.
I'm going to redo these notes again. So I clicked the wrong video and I just jumped into spread measures and I hadn't solved the inconsistency with the notes I have. And the reason why they're inconsistent is because I kind of skipped around a little bit. So the concept of trimmed mean is actually from a previous lecture before even talking about variance and stuff. So yeah. So rewinding into here now.
Adding this observation to a version of the data set, and then computing the median and the mean of that data set. The result will be an R matrix. I take
Let me hop off camera for a second.
locos sound like all in one bowl. With fresh organic greens, fire-grilled chicken, and crispy crunchy goodness, Dos Locos salads are made for every side of you. So you can feel good about what you're eating while still indulging in the cheesy, melty flavors you crave. Try a new Dos Locos salad from El Pollo Loco today.
Gentlemen, now you can find the best brands and fits for you without even trying. Just follow these easy instructions. Step 1. Shop a personalized store that does all the work for you by customizing a selection for your taste and body. Step 2. Level up your closet with the best brands and fits with little to no effort. Not trying has never looked so good. Introducing Stitch Fix Freestyle, your personalized store. We're so you.
All right, actually, dinner plans changed a little bit, so I am going to finish this one lecture because otherwise I will forget to go back to it again.
Transpose of that matrix, but that's the version of the matrix that I prefer. I'm giving the matrix some row names and column names, do some rounding, and this is the resulting matrix, and it's in fact, there is a relationship that we can say in general between mean and median, depending on whether the data is negatively skewed, positively skewed, or symmetric. If the data set is positively skewed,
It's talking about skewed data or symmetric data. So remember, the median is where the data set is divided in half. So if it's skewed, if it's positively skewed or right skewed, the median will be less than the mean.
we're going to have the opposite relationship, where the median, since the outliers are going to be on the left-hand side of the bulk of the data, the mean is going to chase the smaller numbers. So the median will tend to be greater than the mean. And in the case of a symmetric data set, the mean and the median should be approximately the same. In real data, probabilistically, when we talk about means and medians and probability, they will be exactly the same because the distribution of data is symmetric, but in real data, that's never the case. In real data, they will just be close, and what it means to be close is like a symmetric, right? So what would some implications for that? Thinking back to some examples of positively skewed and negatively skewed data sets, I said that a positively skewed data set is incomes. This relationship means that the average income tends to be larger than the median income. And economists generally prefer to use the median income for income distributions because it seems inappropriate to use the median. This kind of gets to the issue of, I'm giving you these competing measures for means, and for measuring the location of a data set. Which one of these measures should you use? I would say use the one that's appropriate, which means, well, here's one thing. When should you use the mean? I would say you should use the mean when large observations.
So right now he's talking about the appropriateness of using either the mean or the median. So in skewed data sets, so let's say income levels in the United States, it is very heavily skewed to the right because you have a few people who make crap tons of money, but it's not really reflective to use the mean because those outliers shift the mean higher. So in that case, economists use the median because it seems more appropriate. So now he's talking about the appropriateness of using different, when is it better to use the mean or the median?
Are allowed to compensate for small means. Let's say, for example, well, here's one thing. When should you use the mean? I would say you should use the mean when large observations are allowed to compensate for small means. Let's say, for example, that you're gambling. If you're gambling, what you care about are your mean earnings and not your median earnings. Because it's okay for you to win nothing 99 times if you win a million, or I guess it also depends on how much this game is worth. But let's say that you're playing a game that costs $1 to play. It's okay for you to win nothing 99 times if on the 100th time you win $1 million. That would be awesome for you. Whereas in that situation, the median would be $0, and if we were judging by the median how what you're doing, you would think you're actually doing poorly.
And then this is where the story of winning the lottery comes up.
To maybe replace or detract from the overall probability and talk about hypothesis testing, there's notions such as most powerful tests, like if your data set was symmetric and you do intuition mean,
It was a teaser to the future.
theoretically what you're trying to measure is the population median, then you should use the sample median. If you're trying to estimate the population mean, you should use the sample mean. In which case you should not be using the opposite. Now, there are some exceptions to this, and we'll talk about this when we talk about probability and talk about
It's related to hypothesis testing and probability.
data set was symmetric and you do a uniform normal distribution, you should always use the mean, even if what you care about is mean. And the reason why that is because, well, normal distribution, the two numbers are the same. We're just going to leave that for now. So all of this was talking about sample results. There are analogous population numbers too. Okay, so I just want to very quickly satisfy. All right, there is another number, another measure for location called the trim mean. So I'm going to tell you about the trim mean. I'm going to continue for you, but then there will have some caveats that you need to get. You probably should not be using the trim mean, and I'll explain that in a second. But the idea of the
So now he's introducing the concept of a trimmed mean.
we have the median, and the median is not sensitive to outliers, which is generally considered a blessing, but it's not always a good thing because it
And he's saying the median usually isn't sensitive to outliers, which is usually good, but sometimes it's not.
feels a little inappropriate to throw out so much data when you're doing median because
So he said sometimes throwing out the outliers is actually a problem, right? Because like, why are they outliers? Aren't they interesting?
once you know the ordering of the data and you know which one or two numbers are in the middle, then the rest of the data doesn't matter, and that feels a little extreme. On the other hand,
And the argument is that part of what's odd about the median is that you order your data and then you technically only care about the two numbers to the left and right of the exact middle, which is a little odd. You have so much data, right?
a little bothered by the mean's sensitivity to outliers. Furthermore, on outliers, you might think, should we throw out outliers? Should we ignore outliers?
So I'll write this stuff down. A median tends to overemphasize a middle, mean too sensitive to outliers and asymmetry.
Outliers, because that's actually kind of what the trim mean is suggesting that we should do. With the trim mean, what we're going to do is we're going to use only we're going to throw out a certain percentage of the data. Like we're going to throw out 10% on the left-hand side and 10% on the right-hand side of the data set. Throw out the 10%.
So he's saying with the trimmed mean, you actually throw out the most extreme 10%. So the 0 to 10 and then 90 to 100%.
Smallest numbers and 10% and the or the so in this data set 10% of the numbers are the smallest numbers in the data set and 10% of the numbers are the large numbers in the data set. That would be the trim mean where alpha equals 1 1 where you're trimming at 10%. So the idea of trim mean is to throw out the outliers.
You're basically throwing out the outliers with the trimmed mean.
So on this issue of whether you should throw out outliers, you should actually think very carefully before you throw out outliers in general. If you're using a trim mean, then that's kind of what you're doing. But let's say you look at a data set and you see that your estimators are actually very influenced by a couple outliers, and you're thinking maybe I should just throw those out. I would first ask, why are you throwing them out? Are you throwing it out because
That's a good question. Why, if you're using a trimmed mean, you're throwing out outliers. And if you're throwing out outliers, like, why are you throwing them out?
numbers from data sets where it's like, that's probably an error. Someone probably entered the wrong number, so I'm going to throw it out. Like when someone writes in the American Media Survey that someone's made $1 trillion, it's like, that's probably not correct. You should just throw it out. If that's what's going on, go ahead and throw it out because the reason why you're throwing it out is just data contamination. But if you're throwing it out just because it's causing bad behavior in your estimators, that is probably inappropriate, and you should instead try to model the outlier or just accept it rather than throw it out.
And his example says if your outliers are actually data corruption. Say someone accidentally put like a person's salary is $1 trillion, that's a problem. That's just bad data, so you can throw it out. But if it's just because it's negatively affecting your model, that's not really a good enough reason to throw out the data. Good points.
Harder about why it is that you are using the mean rather than the mean. I would actually suggest that over throwing the outlier out. But anyway, let's go ahead and compute the trimmed mean for
So now he's sorting the data so you can see which ones to trim.
which is 1. We're going to trim off the smallest and the largest number in the data set.
Yeah, so the way the trimmed mean works is you take the number of samples and you want to trim 10%. So 10% of 10 is 1. So it's trim 1 observation from each end.
That would be 5.15 and 5.96. And then take the average of the two data sets. So, in that case, x bar
And then average.
makes sense. Will be the average of each remaining numbers, where we're summed from I equals 2 to 9, the ordered data set. And that is going to be 42. So the sum is going to be 42.88. Divide that by 8, and the result will be 5.36. So 5.36 meters, because this data set is okay. And R can compute trim means. In fact, you can just use the mean function like we had before, which is going to pass it an additional parameter that tells the function to trim. Now, I mentioned a little while back, you actually probably should not be computing trim means. And the reason why is because when we compute a median, which a little side note, I guess the median, both the mean and the median counts as particular trim means, where the median is like the trim mean where you trim off 50%, and the mean is where is the trim mean where you trim off 0%. So the trim mean kind of generalizes these other two statistics, but you probably should only use those other two statistics. You should probably not use the other. I mean, I guess if what you were doing is instead of taking off 10% on either end, it's like always take off the two largest and two smallest numbers. That could be appropriate from a theoretical perspective. So because basically, as you increase the sample size, the number of observations that you're trimming off becomes very small relative to the rest of the sample. But trimming off 10% at either end from a theoretical standing is a little odd. The reason why is that there is actually a population.
So he points out if you're trimming based off proportion, it's not great. If you're trimming based off of an absolute number, it kind of makes sense because as your sample size gets bigger, the effect of trimming off is reduced because your sample size gets bigger. So if you removed like 1 or 2 entries from both sides, so if you remove 2 or 4, but your sample size is like 200, then like the effect of trimming off is like not as immediate. But he's now going to explain like why trimming based off proportions like not really a good idea.
That we are estimating when we are using a sample mean, and there is a population mean that we are estimating when we are using a sample mean, and both of those quantities are very well understood. But when you're using a trim mean, you are estimating neither of those things.
And the reason is because when you're actually doing a sample mean, calculating sample mean and a sample median, you're supposed to be able to take that and extrapolate to the overall population, right? But when you're doing trimming, it doesn't actually mean anything because you've actually thrown away data.
You're estimating some weird hybrid, monstrous population statistic that we don't necessarily understand. You're estimating essentially a population version of a trim mean, and it's questionable whether that's actually what you want. It seems like a worse of both worlds in that case, because no one can actually, like, why would we talk about the population except for the 10% largest and 10% smallest numbers? Like, that doesn't really make a whole lot of sense. So, for that reason, unless you are actually, I would actually more advocate for like a mixed trimming where you take off the two largest and two smallest observations. Although at that point you probably should just use the mean or use the median. I probably would not use the trim mean. So, okay, so that's it for this section. In the next section, we will be discussing measures of variability. So, I will cut it off here and have a good day.
Okay, cool. So finished out the location measures, spread measures. So the next one is set theory, which is going to be probability. And it's almost 8, so I think it is time for me to eat. So it's nice to hop back on and start streaming again. Hopefully I will do this more in the future, just as a pressure on myself to study. Even, no matter where I am, it's nice to learn something new. In this case, it's more of a refresher, but like you got to keep those skills sharp. So yeah, and yeah, I think maybe I won't do 3 times a week. I don't know how Tina does it. I feel like I have other things I want to do besides be in front of a computer, but maybe I can do a thing where I would like to do art streams again. But maybe I'll have to split that to a different channel. I know people want to niche down. So yeah, okay, cool. I will check in with you all later, and I hope. Oh, I don't know. I can't read that. I'm super sorry. That. Whoever wrote Cyrillic, whoever's got a Cyrillic name, I don't know what that is, and honestly, it kind of looks like you're a bot. So yeah, I will see y'all later. Hope you all have a nice night. If you have questions or suggestions, especially for stats, please let me know. I'd love to hear all the stuff you've got. All right, check in later.